So let's have a look at hydraulic fluids. Why do we have them? What purpose do they meet? First off, they have to transmit power effectively, efficiently to the actuators. We have converted some sort of other energy, some sort of mechanical energy, electrical energy, into this hydraulic fluid in order to transmit power via a system of controls, etc., to some actuators to do some work. So it has to be fairly effective at doing this. The first hydraulic fluid was water, hence the name. Okay, it's talking about hydra, as in water, not oil. Now, water can be fairly effective. It has a few problems. It has quite a few problems compared to hydraulic oil. One of the things we want to do is cool components via the reservoir, etc. Oil can absorb a lot more heat into a higher temperature than water can. So one of the problems with water is it freezes and boils over a relatively short range. It's very good at carrying heat, but the operating temperature it operates over is relatively small. We want to be able to lubricate sliding or rotating components. Oil is way better than water doing this. Okay, we want a fluid that will be able to lubricate because our components are generally metal on metal. We need to be able to lubricate those items. They're going to have very small tolerances between those items, though. So oil can act as a seal. Now, as the pressure in our system increases, we need to shrink that gap between those metal items smaller and smaller in order for oil to be a good seal. A very small amount of leakage at 10,000 psi is absolutely great. However, I need tolerances of less than 10,000ths of an inch, or less than 1,000th of an inch, sorry, way less than 1,000th of an inch, in order to have that oil operate as a seal. And the last thing we've got here, we can clean it by carrying contaminants to the filters in the reservoir. Anything that builds up in the pipe system, okay, from overheating, from excessive use, from bits chipping off, we want to be able to carry that away from the operating part of our circuit in order to extend its life and filter those out in some manner, much like we do with a car engine. We have a filter designed to filter out contaminants between oil changes. The fluid needs to be compatible with the seal, the hose materials, or the other materials. We don't want that fluid breaking down the seals. Otherwise, it just all leaks over the floor or creates contaminants in our system. We want it to be able to expel air. This is also called resistance to foaming. Air that becomes foamed, like say in your sink, if you've got too much dishwashing liquid, that air becomes entrapped into the system and then could possibly get sucked through the rest of the system, causing poor performance. We want it to expel water. Here's a word that you can't use in Scrabble. It's not in the Scrabble dictionary. Demulsify. It's an actual word. What it means is to eject water, to throw water out. Okay, so ideally the water will drop to the surface, to the bottom of the tank, because oil is lighter than water. Excuse me, but the water will quickly drop away, and then we have designed our system such that the water that does accumulate is drained whenever we drain the reservoir. There are some systems, I've seen systems where we operate in environments where there is possibly a lot of water in our system. We run a separate filter to get that water out, okay, off the bottom of a reservoir. We want to be able to operate over a wide range of operating temperatures. If I'm using hydraulics in northern Canada or in Russia, it's cold. Okay, so we want this to be able to operate at minus 60 degrees. Wow, that's a bit tough. Okay, we want to be able to operate at the high temperatures that we'll typically see our systems run at, 85 or 90 degrees. Ideally, we're going to operate in a narrower band and choose an appropriate fluid. But if I'm operating in an extreme cold environment, it does pose problems for getting a fluid to operate that cold, because it's also going to operate typically in the 70 degree range, at least when it gets hot. Now, hydraulic fluid compressibility. One of the reasons we use it is because it's virtually incompressible. Okay, and I say virtually because there is some small compression. At 1,000 psi that we typically run our trainers at, it's 0.4%. You're not going to notice 0.4%. 3,000 psi, which is pretty typical for most industrial systems, it's going to compress about 1.1%. Still not really measurable with the gauges and things that we have in our system. So that's why we say virtually incompressible. Because it's virtually incompressible, if I push the fluid at one end, I've got 200 meters of hose, it responds at the other end pretty quick. So our systems don't usually have 200 meters of hose. It's a crazy example, but generally we're going to find very good responsiveness out of a well-tuned, well-maintained and designed hydraulic system. Sluggishness does occur due to contaminants and things wearing out, but generally they're going to be very responsive to us. So the first point, lubrication. Why do we want to lubricate? Because we've got metal on metal moving parts. Okay, so we want what they call full film lubrication. That would keep the moving parts apart. There would be no contact. Now, if I've got little peaks in the surface, and I've got a diagram here blown up of two surfaces with the red oil between them, no surface is perfectly smooth. Not in hydraulics anyway. That would just make it unrealistically expensive to be able to build these items and use them. So there's going to be divots, there's going to be peaks, and what happens is the peaks can come into contact and wear with each other. That's going to create heat, which is kind of an enemy. It's going to create a very localized heat. The metal is going to heat up, the oil is going to heat up, the oil is going to fail real quick, but just a little bit of oil at that point. Also, bits could chip off and go through our system and cause damage to seals and things like that. So one of the points of this fluid is to create lubrication between these moving parts, ideally holding them apart so they don't actually come into contact. As the pressure required in the system increases and increases, I've got more chance of blow-by, slippage of oil leaking between components within the system. These components could be things like our actuators, our motors, our pumps, even our valves could be points where this would occur. So as a consequence of what we've done in our design is we've made the tolerances really, really tight on the manufacture of these items such that the gap is really, really small. Really small gap, more chance of metal to metal contact. So we talk about boundary lubrication. What happens at that point? Okay, we get galling of surfaces. Okay, galling of a work surface adds heat. Work hardens the material, okay, which will make it fail usually in a worse way. We usually design these to have a particular hardness. Also, as I add heat, oxygen in the system will cause rust. Over a certain temperature, I think it's 60 or 70 degrees, we'll probably talk about that later on in contamination. Every 10 degrees increase in temperature pretty much doubles the amount of rust that could potentially occur due to oxidation. So we want to keep those temperatures reasonable, try to keep the amount of oxygen, water, etc. down in order to prevent damage to our system. Now, those of you who have done some work with automotive oils and things like that know that we have additives in our oils and greases. We have EP additives, okay? These are for extreme pressure. We used to have anti-wear, or we still have anti-wear for lower pressure items. But we have these same sort of additives that you have in your oil for your car. We put the same additives in the petroleum-based hydraulic fluids to improve that performance. Now, for a lot of them, they're a zinc compound. Zinc doesn't match some of our materials, so it's a bit of a choice to get the right additive. The idea is that the additive in the oil will come out of that oil in certain conditions. For instance, when there's too much heat, okay, it will bond to the metal nearby. Or if there's too much pressure, and it will bond to the metal nearby, thus creating a barrier that is not solid. What it does is then creates a smaller gap for the fluid to flow through. That boundary flow condition is quite small, and I can get fairly good pressures through there, a film of oil that provides a seal for my system. So an EP, additive extreme pressures, there's also anti-wears and other things like that. They all work kind of differently. They're made of different materials. But the EP one is typically what you're going to see nowadays, anything over 3,000 PSI, I suppose you're going to see that. Now, it's an important comment here, the last one. An additive's life is shorter than the base fluid. Okay. So a hydraulic oil, like we have in our trainers, I would expect that oil to easily last a number of years. In fact, the oil in the trainers is 6 years old currently, and we've requested that it be changed. The oil itself is pretty good. It's pretty clean. If you look at a drip on something, you see how clear that oil is. Problem is the additives in that oil have all broken down and no longer exist. They're fairly short life. Generally, 2 years is a pretty good life for an additive. Much like gasoline. Gasoline in your car, after about 3 months, that gasoline, most of the additives in the gasoline have evaporated off, and you don't get very good performance out of that gasoline. When I was a child, that number was about 2 years. We had different additives. Yeah, a lot of the additives we used when I was a child were pretty toxic. And the modern additives that we use that are safe for the environment and the user tend to have a very short shelf life. So it's exactly the same with any hydraulic fluid. The additives have a fairly short life, and that's really why we change fluid as often as we should, as we do. Talk about how it seals. I've got a fluid going through a tiny gap. You think, wow, how does that seal? Think about viscosity and temperature and things like that. There are obvious things to impact how it seals. Imagine trying to suck honey through a straw. Fluid with a high viscosity compared to sucking water through that straw. Okay, it's going to behave very differently through that same gap. Tighter straw, smaller straw, it's a lot harder to suck the water through. Or a milkshake. If you go to Peter's and get a milkshake there, fairly thick straw they give you to suck that through. A thin straw wouldn't do it, okay, because the viscosity of the fluid has changed. So these internal clearances do allow for some leakage through there, but the absolute ideal, is that there's just enough oil in the boundary condition to prevent the metal from making contact, okay, but also to prevent the oil blowing through that joint. That would be the ideal world. It doesn't exist, but that's what we strive to do in our design. So we like this fluid to minimize leakage within the components. Okay, any fluid that leaks through the components is fluid that's not doing work for us. It's fluid that we created flow for at cost that we're not getting any work for. It's fluid that we put an energy into that has to get rid of the energy somehow. That energy pretty much goes away as heat, which causes us problems. So getting rid of slippage or internal leakages, it says here, is something that we want to do by good design. So the sizes of these clearances, the pressure of the fluid, viscosity of the fluid, we talked about with, say, honey and water, will make a difference. The picture here is showing inside of a large pilot operated DCV, and the red indicates that boundary condition where I'd expect a small amount of fluid to leak by, but also provide a seal as we operate this DCV. Cooling, we want to be able to cool this fluid, okay? We transfer the heat away from the working elements where the heat was passed to the fluid to an area where the heat can be released, i.e. the reservoir or a heat exchanger if necessary. A well-designed system, Mother Nature does that for us. Mother Nature charges us very little as long as we design things. Consideration here in your design, imagine a double port cylinder, okay, and I've got long lines to it, to this cylinder. Say this cylinder holds a gallon of fluid. If the long lines to that cylinder hold another 3 gallons of fluid, when I retract that cylinder, I push a gallon of fluid into the lines. I push a gallon of fluid out of the lines. So a gallon of the fluid that is now in that line has not been filtered or cooled. And then when I next extend it, I extend that dirty gallon in, okay, or some portion thereof, okay. That's going to result in fluid that burns, fluid that gets very contaminated. For those of you who have done the brakes on your car, when you release that little knob there, the 10 mil wrench or 3/8 wrench, pump out a little bit of brake fluid. It's extremely black. Okay, and that's because of the oxidization that has occurred as a result of that fluid overheating. A brake does not have a path for that fluid to go back and get filtered. It gets worked within that brake cylinder, backwards and forwards all the time. This is why we need to bleed our brakes, because that fluid never got filtered. It has been at the working end of our system, getting dirtier and more overheated and breaking down compared to that nice clean fluid in the reservoir or going through the pump from the pedal if you've got an older vehicle. Okay, so that's one of the considerations of our system. We don't want to be bleeding off dirty fluid all the time. We like our fluid to come back and get cleaned and cooled in order to extend the life of that fluid. Now, we want to continue preserving the life of that fluid. We can do this things like having baffles in the reservoirs. We talked about that last week. So we can have coolers, heaters, filters, and strainers. We do this to extend the life of the fluid. We invest in some equipment, just pay good money for it to make the fluid last a long time. Not only that, the fluid is going to be safer to use. It's going to make your equipment last longer if it's nice and clean. I'm going to have better runtime, etc. if I take care of my fluid. It's like taking care of the blood in your body. Okay, if you get blood poisoning, it's not good. Same with the fluid. The fluid starts going off. It is not good. In fact, the fluid can even go rancid. It can get infected. Thankfully, it runs hot, so that doesn't happen very often. Usually when that happens, it's in an idle system. Now, hydraulic fluids. We talked about hydraulic fluids and some basics of what do we need out of a fluid. Let's have a look at the properties of a fluid that naturally exist in a fluid. We want to look at, it has viscosity, okay? That's a fact in the fluid. It has what we call a viscosity index. How much does the viscosity change with temperature? If I want to operate it over a wide temperature range, I probably want something that doesn't change a lot with temperature. What's the pour point? At what point can I start to get it to flow? I have to suck that fluid up out of that reservoir, or even if I've got the fluid and I've got a wet pump, I've got to get that fluid flowing. If the temperature is so cold it doesn't want to move, okay, we're going to have cavitation and issues. So that pour point becomes important. The ability to lubricate, I've beat that to death. Oxygen resistance, I spoke to that. We'll get to that more. The anti-wear capabilities, natural fluid does. The compatibility with the system elements. No fluid is 100% compatible with everything. Rust and corrosion protections. In hydraulics, sometimes we talk about corrosion as one thing. Sometimes we add in rust. Rust is specifically oxidization. Corrosion is a chemical reaction, usually with an acid. So sometimes we talk about them differently because I have to have different additives in my oil to accomplish improving the performance of rust or corrosion protection. And then demulsibility, this ability to get rid of water. So first off, viscosity, resistance to flow. You've probably all covered this. Okay. Low viscosity, it's very thin like water. High viscosity like molasses or honey. I've got a graph here, and in yellow is the mechanical efficiency of a system. I think of a system rubbing against each other. Okay, when I've got low viscosity, okay, it's pretty efficient. Okay, excuse me, it works well. But if I have two systems rubbing together, they're sitting in honey, then that's not going to provide me great efficiency. Okay, they're going to tend to rub together. It's going to push the honey out of the way. I'm not going to get a film between them. I'm going to get mechanical wear and tear. And we talked also about the ability of volumetric efficiencies. Okay, so volumetric efficiencies with low viscosity tend to be pretty poor. Okay, it leaks really fast between two mated surfaces. Okay, but if I've got something like honey and I try to blow it through a straw, it doesn't want to go through there. Okay, and that's the green line in this graph. So the overall efficiency, multiplying the two together, which we did 3 or 4 weeks ago, I get this red line, overall efficiency. And my viscosity wants to operate, ideally near that peak range. Okay, in a certain range is where I want my viscosity to be. So I'm going to choose a fluid that's going to give me good performance, good overall efficiency of my system. It's a balancing act between volumetric and mechanical efficiency to get that overall efficiency. So what does this mean? Like molasses or honey, okay, it's going to require increased work to get it to move, okay, more energy to make it move. As I try to move it though, okay, I'm going to have increased temperature due to friction losses. I'm going to get greater pressure drops across an orifice, okay. Imagine trying to blow water through a straw compared to honey through a straw. It takes a lot more pressure to do that. I've got a greater pressure drop to get honey through a straw. It can be slow, it can be sluggish. As the viscosity gets higher and higher, the whole system kind of slows down to less efficient. Separation of air. You've probably all seen honey with air bubbles in it, even when you buy it fresh off the shelf. It's pretty tough to separate all that air out. It's kind of trapped in there in bubbles within that honey. Very high surface tension on those bubbles caused by the honey. And then the worst one for us is that pump cavitation. You try sucking a fluid like honey, you're going to create quite a vacuum. And then as we're going to see, that cavitation resulting in lots of small bubbles that break down and cause problems with our system. Also, if the viscosity is too low, what are we going to have? You're going to have increased wear and tear, increased internal leakage, more blow-by in my pumps, my motors. So I'm going to lose efficiency in my system. I'm going to get more increase in operating temperatures, more slippage, more leakage, more fluid that I've pumped energy into that's got to get rid of that energy. It's going to be heat. The cylinder blow-by, increased cycle times, once again sluggish. Any fluid escaping from my actuator or my pump is fluid I can't use. It's going to take longer to complete a cycle or a process. Viscosity can be measured in different ways. Different industries prefer different methods. Now, I don't know if you learned about this in physics. We call it dynamic viscosity, or absolute viscosity is another term for it. We measure that in centipoise. And one of the problems with that, it doesn't account for temperature, where a kinematic viscosity does account for temperature. So that's a little bit more popular. Within hydraulics, we tend to like this system, Seibelt Universal Seconds, SUS. It's a very good method of measuring viscosity, very precise method of measuring it. It's really nice to have a measurement system that kind of aligns with the use case, okay, and the SUS does. SAE numbers with motor oil is very common. We've all seen those. We can talk about those in a little bit more detail. Or ISO, okay, International Standards Organization. They've got standards for nearly everything. They've got standards for viscosity grades. There's a based off kinematic viscosities. Growing a little bit more popular, but to be honest, in the hydraulic world, not very fast in North America. So Scott here, most systems run with an oil range of 150 to 300 SUS, okay, and a typical ISO grade of 22 to -68, okay. These are the ranges that we typically use for our hydraulic oil. Typically in industrial applications, we're going to use an SUS number. Also discourages people from using the wrong oil if we use a different method of determining it. So absolute viscosity, I'm just going to fly through this real quick. Boom, it's done. And you should all remember that from science. It's the resistance, it's the shear force to make one layer of fluid move over the top of another layer of fluid. Okay. Kinematic, we bring into temperature. We have to acknowledge viscosity changes with temperature. And this is why kinematic is better in an environment where you've got lots of different temperature changes. Generally, the previous one, I'm going to specify 1 or 2 temperatures. Still going to do the same with kinematic, but it allows us to think about temperature and density and things like that, still based on shear force. SUS, a little bit more complicated. Hydraulic oil heats up, okay, and generally is going to have an average heat through the system. It's going to heat up as it gets through the system, gets to the reservoir, cools down, heats up again, goes through that cycle. So the SUS, what we do is we take a very specific quantity, usually about 60 mils of fluid, and we time how long it takes to get through a specific orifice. Now, the dark blue here is the hydraulic oil, and the teal color there is an oil bath. So we heat up the bath, we have an electric heater, and we heat that up. We heat up the mechanism, the orifice where that oil flows through. And then we've got up to a temperature that we want to use it. We open that orifice, and then we start timing how long it takes, say 60 mils to get through. So the reality is I might have a stopwatch that's going to start when 10 mils have passed through, and I'm going to stop it when 70 mils has passed through. So I don't have a source of error of the opening and the closing of that valve. My source of error is my ability to measure 10 and 70 and to respond and start the stopwatch. So this is a very good system because it actually produces the oil up to a temperature, puts it through a small orifice, which is what is happening when we're leaking and providing lubrication. So it nicely aligns with how we actually use the hydraulic oil, which is why, personally, from an engineering perspective, I prefer this system. The fluid will flow slowly. Think of molasses, it's going to flow through a small orifice really, really slowly, even if you heat it up. Generally here, we've got two temperatures ranges we're going to test, 40 degrees C and 100 degrees C, well outside of the typical operating range. Typically, we start a piece of equipment up. We're not going to run it until we get 50 to 60 degrees. We want to keep it under 85 degrees. It's well within the band of our operations. So we're going to get SUS numbers for that. It says here at 40 degrees, hydraulic oil, around 150 SUS is a target. As it gets higher, maybe 200 SUS. But look at this range. I shouldn't go below 45 SUS or 4,000 SUS. So another good thing about this is it gives a very big range to actually do this operation and measure the performance of the oil. Now, for extreme temperatures, extreme cold with extreme hot, or extreme cold with normal, we want a multi-viscosity fluid. These are more and more common nowadays. 50 years ago, weren't many multi-viscosity grade fluids. They were very poor performers compared to a fluid today. Multi-viscosity grade fluids are really, really good ones. They're not pumped out of the ground. They're a synthetic that we have refined and then blended in order to get the properties we want, along with a whole bunch of additives. Okay, so oil typically isn't a multi-viscosity grade item, only over a small range, not a big enough range for what we want for hydraulics or even motor vehicles nowadays. Now, viscosity index, I'm racing through this because we don't have a lot of time. Viscosity index, I've just got here a high and a low one. Okay, a high viscosity index, good. I want virtually constant viscosity across a temperature range, especially if I'm operating in Canada where I get low temperatures. Even here in Calgary, it may be cold outside, it may be warm inside, who knows, I'm bringing the oil in, have to use it. Or even in Mexico, dealt with a situation 8 years ago, 9 years ago, a facility in Mexico, northern Mexico. It got so cold, people's houses had pipes freeze. Really, really unheard of that it was that cold. Well, we don't heat our buildings that much in environments like that. We're usually interested in keeping them cool for 9 months of the year because it gets so hot and humidity is so high. So we had lots of problems with hydraulic equipment just underperforming because of this, and it was just heat it up and run it. Okay, get it really warm before you actually start using it. Viscosity and temperature, we've talked about how they are interrelated. Temperature change causes viscosity changes. I've talked about that in a few previous weeks. Right here, excessive heat at the bottom. Okay, excessive heat can also destroy the oil through oxidization, which can cause what we call varnish. Okay, think of varnish as being a hard coating on a surface, sludge, muck, mud, think of things like that, or corrosive acids, so fluids running through our system with the oil. They can be created very easily and work against us a lot more effectively when the temperature gets too high. Okay. SAE, Society of Automotive Engineers, probably the ones that you're most familiar with if we talk about viscosity in industry. We have two grades that we use in North America. In fact, most of the world still does this system, follows the North American standard here that was established a long time ago. We have numbers with a W at the end of it. Those numbers at the W mean specifically a winter grade, okay? And that is measured in absolute viscosity, absolute method, okay, centipoise. And then in the summer, we measure a different system. We use kinematic viscosity. I don't know why SAE decided to do it this way. This is just the standard that we use. So basically, it's designed to operate at certain temperatures. So we have 0 degrees F, okay, so minus quite a bit in the centigrade, through to 210, 100 degrees. This really gives us an idea of how things are going to perform over the operational conditions of most of our hydraulics that we're going to have here in Canada. The winter numbers have a W on the end, summers do not. When I was young, you would not typically buy, say, a 5W50 oil. That blend did not exist. A multi-viscosity oil might be something like 3040 was probably the most common. Didn't even include a W rating, unless I got really, really low and had like a 20W20 or something like that. Nowadays, we buy oil that covers this entire range, 5W to 50 viscosity for our engines. We just put it in, we use it. We don't change our oil based on the seasons anymore, okay? Because the quality of the oil, the synthetic oil, is far superior to what we had even 30 or 40 years ago. So it's an interesting way of looking at oil and comparing it. We can do this with hydraulic oil. We can give it a number as well. But then if I do that, people start trying to use engine oil in their hydraulic systems. The international standard based on kinematic viscosity, based on a range of viscosities, okay? So I might have a ISO OVG 46 here. It's on a range from 41.4, I don't know why they came up with that, to 50.6 kinematic viscosity at 40 degrees C. So a relatively good oil to use in a hydraulic system. We can compare them very easily. Now, this blue band is my ideal band of viscosity for, for hydraulic oils. If we look at this, I'm going to look at the ISO viscosity grade, 46 is good. Look at gear oil. Gear oil, sometimes people will use gear oil, sometimes people will use crankcase oil in their systems, just because I need to top it up. If you're ever in that situation, my recommendation is to use automatic transmission fluid. Okay, automatic transmission fluid, it's a little high up here, up above 80, but it is a better fluid to use than gear oil, regular gear oil, or crankcase oil. ATF fluid does work a little bit better. I can buy that in a 1 liter container very easily at most gas stations, and just top up a system. If I've got a small operation and a little bit of oil every couple of months or something to top a system up, that will work instead of buying hydraulic oil. Hydraulic oil is cheaper, okay? Sometimes it's a bit of a pain to get hold of relatively quickly. Okay, now I talked about some of these things earlier, okay? The pour point, get it flowing, get it running, okay? What's oxidization resistance? Oxidization is bad for me. Rust and corrosion prevention, they're bad things. Demulsibility, ability to throw out water. I'm going to add another one here, fire resistance. I don't really want to have fires, okay? If I've got a fire, I'd like this stuff to not burn too badly, or even to go out if the source of ignition is removed from my fire. Okay, so these are natural qualities of fluid, not very good, some of them, and we want to maybe enhance them, but they are some natural abilities. I mean, fluid, hydraulic oil doesn't like to burn unless you get it up to temperature or start to vaporize it. Okay, these are properties of a fluid. Pour point, that lowest point at which it will pour. For me, really, it's about in the reservoir. I want it above that temperature in order to be able to get that fluid to suck up and flow through the system, start creating flow. Typically, we judge this to be about 10 degrees below the lowest expected temperature in our system. That's caused a problem in Mexico because we exceeded that 10-degree mark, and the hydraulics wasn't really designed to run as cold as it got a few years ago in northern Mexico. Manufacturers are really good. They specify what you should be using. They love to do that because if they catch you not using it, they will void your warranty. Okay. Oxidation resistance. Petroleum oil, vegetable oil, okay, they can oxidize. They will start to break down into typically an acid, which is going to give us problems. Okay, they're going to cause corrosion through the system. They could form gums and varnishes and sludge, which block things from flowing properly. And therefore, if it's blocked something from flowing properly, I may have a heat problem, a sluggish response, things like that. So operating temperature, generally want to keep fairly constant. I want to get it up to temperature and run a system at temperature in order to reduce oxidization, but to keep that temperature, if I can keep it down to 60 degrees, that's fantastic. Things that cause oxidation in general. Heat will help improve or increase the rate of oxidization. Pressure increases the rate of oxidization. Water, that definitely helps with oxidization and rust and things like that. Metal surfaces, they want to rust, they corrode really easy. Agitation, stirring the liquid up, that increases oxidization. Contaminants in the system, that increases oxidization. Well, welcome to hydraulics. We got all 6 of those. Okay, we have just created that perfect storm environment for oxidization to do its nasty little things in our environment. So we've got this perfect storm of elements that will increase the rate of oxidization. So we need to control these very, very carefully. Here it says temperature below 60 degrees, oil oxidizes really, really slowly, and it's going to double here for every 10 degrees Celsius above 60. So when I move from that 60 to 70, which is a typical operating range, it's going to double the oxidization rate. Up to 80 degrees, it's really at the peak of the range I want to see. It's starting to get bad. 4 times the oxidization rate. That's why we want to, we keep saying keep it down below 83, 85 degrees Celsius, because we're really starting to worry about oxidization at that temperature. Rust, corrosion prevention. As I said, rust, to talk about rust as being specifically the oxidization with a metal. The picture in the bottom is a vein pump like the one I showed in the lab, showing signs of surface rust. Okay, that rust will occur and then it breaks off. Now I've got these little bits of iron oxide floating through my system, jamming things, bouncing off bits of metal, causing other things to break off. Not a good friend to have in the system. Whereas corrosion, we think about corrosion in hydraulic systems as something that's happening with an acid. It's not particular to the rust. It can impact other metals as well. So particles of metals wash away, okay, contaminating our fluid. We want a good filter system to catch these the first time round, but they'll still do some damage before they catch their way to that filter. Demulsibility, the ability of fluid to separate or reject water. Okay. Now, this is not as much of a problem as you'd think in Canada because it doesn't generally get to really high humidity. People talk about humidity in Ontario and things like that being high in the summertime. It's not like living in the tropics where typically we hit 80% through 95% humidity most of the year round. So as the oil and the air in the reservoir cools at the end of shift, the ability of the air to hold that water decreases. And when you've got 80, 95% humidity, you will get water dropping out of that water, okay, forming dew, condensation, and falling into the fluid. So it is more of a problem in those sorts of regions. But we want our fluid to get rid of any water very easily. Leave it in the bottom of the reservoir. Fire resistance. Fire resistance depends on the state of the fluid, okay, the temperature of that fluid. As it increases, it's more and more likely to burn, okay? If I atomize the fluid, a burst hose spraying fluid, I've got a smaller surface area around each drop of fluid. Therefore, it's more likely to catch fire. If I've got the vapor of the fluid, even more chance of catching fire. So these numbers here are actually given for fluid itself in its liquid state, in bulk, as it were, in our system. That flash point under which the thing will catch fire, or the lower explosive limit in industry, can be as low as 93 degrees. Okay, but typically we want to arrange that to be a lot higher, well above our working pressures, well above the temperature of anything in our system. We want to keep it fairly high so it's less likely to cause a problem. Now you've got to know your environment. So where I've got a lot of hydraulics, I don't want anyone welding. We will do a hot work permit. Typically industry will do a hot work permit, but you've got to get a permit. You've got to put up shielding and all this sort of stuff to do any welding near this. Now, when we repair our equipment, now we've got the problem that we're trying to weld right where our hydraulic oil is. We want to get rid of any vapor, because the vapor is more likely to catch fire. It's much like welding a fuel tank on a car. It's a lot safer to weld a full fuel tank than an empty one, because the fuel is less likely to catch fire and explode on you. So know the environment. There are a lot of government regulations about working with hot items like welding. We may design our building. We often design our building such that we have a concrete wall or a cinder block wall around certain areas of our building to keep things safe in case there is a fire. Fire point temperature, continuous burning. Fire resistant fluid will not sustain combustion when the ignition source is removed. And that can be huge saving. Something can be burning. For instance, the roof of my house was burning about 5 years ago when the neighbor's house burnt to the ground. Soon as the fire department suppressed the flames on the house next door, the fire on my house went straight out. Okay, the roof just resisted. Soon as the source of ignition was removed, the fire goes out. And that's a good thing to have in a hydraulic fluid. It means I've got less fire to fight. Just fight the source, not everything else. And then the fire should go out on the fluid. Additives. Talk about additives. What do additives do? Additives enhance a natural property. Okay, they enhance a natural property. Think of putting lipstick on a pig. Pig ain't a beautiful animal. Putting lipstick on it does not make it more beautiful. Okay, it's an additive. Okay, only works when it enhances an existing property. It's no good trying to give it a property it never had. Okay, so that's what we do with our hydraulic oils. We know that they do inhibit rust and corrosion. It's an oil. They know they do inhibit oxidization. They're good at throwing out water. They're good at preventing wear. Pretty good at preventing foaming, releasing air. Generally have a pretty good velocity index. But we can improve all of these. We can all improve these and make the oil better for our use by adding chemical additives. So that's what we do. We add them to improve the oil performance and the life of the oil. Rust inhibitors, so we talked about how the EP works. Okay, typical sort of thing where it's going to coat metal parts so that natural air and moisture do not interact with the oxides. Okay, it's like painting something that we're going to use outside. We paint metal to prevent rusting. It's the same thing here with the fluid, except we have some sort of inhibitor within the fluid that's going to help prevent rust occurring. Corrosion inhibitors, preventing acids from forming. Certain parts of the world, we don't use aluminum siding because of the high sulfur content. So in some areas of Alberta, where we've got a lot of H2S off-gassing from wells and out of the ground even, aluminum corrodes really, really quickly. So we don't tend not to use it. Okay. Some metals, such as alloys containing magnesium, lead, and zinc, are very susceptible to corrosion. Magnesium, not so bad. Lead is toxic in a lot of forms to life. Zinc is going to cause us problems in our hydraulic system sometimes. So we put zinc in maybe as an anti-wear additive, but then the zinc breaks down as the additive breaks down, and then causes other problems in our fluids, causes corrosion. So we have to put in another additive to prevent the first additive when it breaks down, causing us problems. Antioxidants, we just want things that's going to help get rid of the oxygen in the system. Okay, some metals such as copper, that's going to oxidize very easily. Okay, copper's in brass, it will leach out of brass. We tend to not to use brass much in our hydraulic systems, unlike our pneumatic systems. We use it all over the place. We tend not to in our hydraulic systems. Emulsifiers, we want to get rid of the water. We add some additives to improve that performance of that oil, make it get rid of the oil, dump it into the bottom of the reservoir. From an environment where there's a lot of water, okay, we want to be cognizant of that water maybe freezing and then preventing fluid from being pumped up through the pump because it's operating in a layer of ice. I did have that once someone called out, we went out to the equipment and had a look at the filters, and there was a filter at the bottom of the tank that was just totally caked in ice because there was so much water in the oil. Anti-wear additives, wear resistance, extreme pressures, these are just things to improve the lubrication ability of the oil. Most of them perform some sort of surface when exposed to a little bit of heat or something like that. EP comes out of solution exposed to high friction heat. Okay, so EPs tend to be on our high pressure systems where I've got very tight clearances between my metal to metal parts. Most common anti-wear is a zinc dithiophosphate. Okay, but that will break down to cause our problems. If I want an oil to last a particularly long time, I'm not going to use that. I'm going to use a sulfurized olefin instead in order to get something that breaks down into a non-acid. Anti-foaming agents, we don't want foam in our system, trailed foam in our system. That is just going to cause oxidization. So we put anti-foaming agents to break down the surface tension on the bubble. Okay, we reduce the surface tension on that bubble, allowing it to break more easily, and therefore foam will not occur. Foam can occur because air leaks. Okay, a system not sealed properly is going to suck in air prior to the pump and will cause us a problem. High velocities through orifices, spools can cause us problems. It's going to cause cavitation to occur. Rapid discharge of accumulators can cause air to come into a system. What they can do is they can combine to big bubbles and cause sluggish system performance. They could also collapse, causing corrosion or erosion, causing erosion and therefore a corrosion point. VI, velocity index improvers, help prevent waxes from forming crystalline structures at very low temperatures. Think of honey. Honey, if you leave it in your cupboard or your shelf there for 2 or 3 years, you're going to see it starts changing. It gets very crystallized. Okay, we want to not have that happen. What do we do about it? Well, if you take that honey and you put that jar in a pot of boiling water for a few minutes, you'll find that crystalline structure breaks down, much like would happen with a VI improver. Okay, so this wax can come and go, but it never really goes 100%. If it's been waxed once, it's going to form wax again a lot easier at a higher temperature. So generally we want to avoid that. So we'll get VI improvers, velocity index improvers, to give us more even performance across temperature range that we're operating at. No fluid is perfect. None of us are perfect. Okay, they may be good for an application and not good for another application. Certainly not going to be perfect. It's a compromise game. I've got all these things that fluid needs to do, and I've got to choose which are the most important for my application. I can compensate by changing the fluid more often in some cases. Okay, so aircraft, submarines will have certain things that are really, really important, like it doesn't catch fire. Okay, that might be absolutely critical. for something that's 29,000 feet in the air, but not as critical as for something sitting on the ground. So there's going to be compromises made on the fluid in order for it to perform safely and effectively in the environment. Now, environmental concerns have caused an increased interest in biodegradable fluids for hydraulic systems. Biodegradable is a word I do not like. Okay, and it's a word I do not like because people of my generation, 40, 50 years ago, we were taught biodegradable is good. Well, what does biodegradable mean? It means it breaks down in the environment. What does it break down into? Is it something safe or not? There's a lot of stuff out there that's biodegradable that breaks down into poison, toxins, okay? So we've got to be really careful. It's not just biodegradable fluid, but when it does degrade, it doesn't degrade into something that causes harm in our environment. Okay. The rise of synthetic water-based fluids over the last 20 or 30 years, as we've got better refining and controlling our refining process and blending to create synthetics, we can custom order, I suppose, hydraulic fluids, but they're still not perfect. They are still far better than their ancestors are. But they are typically heavy. Because of that, we've got to consider that our pump, we couldn't run a system very effectively in our lab with a synthetic or water-based system because our pump sits above the reservoir. We could run vegetable oil, that would be perfectly fine, that would work great, or we can run petroleum oil with that configuration, but we can't flood the pump, so a synthetic or a water-based system wouldn't work. So generally, what have I got? I've got three categories, okay, when I've got to think of this in a use situation. Fire resistant. I'm fairly big on that in certain industries. Okay, that's going to be the most important thing, to have a fire resistant fluid. So Canada's submarines and their warships and things like that that the Navy has, we generally find that fire is a bad thing to have on something like that. So we'll tend to use fire resistant fluids more than say maybe on a civilian ship, even though there's lots of passengers on them maybe. Petroleum oils, very common. They work very well. You know, we've been using them since about the 1890s when we decided, hey, there's a lot of oil available and in the ground. Instead of using water, we can use those. Biodegradable fluids, vegetable oils, polyol esters, things like that. That's the third category that we'd use. And some interesting oils within that category. Hydrocarbon-based petroleum oils are cheap, relatively easy to get. There's a lot of it. They provide good lubrication, readily available. Oil, pure oil, hydraulic oil, when it's in the barrel, is relatively low toxic level. Okay, wouldn't advise drinking a couple of gallons of it, but it's not going to kill you that fast compared to when it's been used. When it's been used, it's got all these acids and these oxidants and it's other chemicals in there that are not really healthy for you. But it's a relatively good fluid to use as a starting point. We blend them now for specific applications and get very, very good performance out of them. ATF, sometimes used in hydraulic systems, not really good at high temperatures, but we're not usually running it at that high temperature. Often it's just for a top up in our system. They are a little bit more expensive, but when you're only buying a liter for a year's worth of use, it's not a big deal. Okay. Having a look at the oils compared to their SAE numbers. A typical environment that I may want to use in Canada, well, that's probably the second line down for a lot of industrial applications. Any of those bottom three lines, you're going to see here we've got 5W, 5W to 20, 5W to 30, or 10W, 10W to 30. Various viscosity ranges that we could use, but I would not recommend it because it doesn't have the appropriate additives in that oil, that motor oil. Water-based fluids. So really good because water is really hard to make burn. Okay, some of the additives and the other bits and pieces in there will make it burn. So we could have what's called a water in oil emulsion. more oil than water. Oil and water emulsion, or safer bet, a glycol. Now, these items have a very high weight per gallon, so therefore specific gravity. So we want to use some sort of flooded inlet pump, like the vertical orientation reservoir that we looked at last week. They're a good candidate for using water-based fluids because we don't want things to burn. They will, however, have more problems with rust, etc. Phosphate esters, they attack a lot of plastics and things that we may use in seals. Okay, paints that we may use to line the tank. Okay, when I make a reservoir, it's not put into service straight away. Might be shipped somewhere, might sit on a shelf somewhere, might be installed somewhere 6 or 8 months later, might have traveled through the tropics to get there. It's going to have a coating on it in order to prevent it starting rusting. That paint will flake off eventually. We don't want it all coming off in big pieces. We want to be able to control that. Phosphate esters require special seals. Okay, Viton, that last word, Viton, we have to be very careful with Viton because Viton is used in a lot of industries for the military. I need to use Viton in order to really have an effective method of upgrading plutonium and uranium, hydro or flexofluorine, whatever that we use. I've got to use Viton seals. So Viton export is banned to a lot of countries. And in Canada, there was a company here in Alberta that I'm going to guess now 7 years ago ran afoul of export laws because they exported a bunch of stuff to Iran, not for the nuclear industry. But the reality is the customer could then take apart the equipment, take the Viton seals out and put it into the nuclear processing equipment. Therefore, violation of Canadian and US and many international sanctions at the time. So that company got prosecuted and a couple of people went to jail over it. So always very careful when it comes to Viton. It's a great material. It works really, really well, especially in high temperature applications, but it is used in some industries that are subject to sanctions. Synthetics, that typically blends. They can attack lots of different things in our system. Generally, the advantages of synthetics outweigh the disadvantages. Some synthetics are petroleum capable. I would say don't mix them. You can go online and see all sorts of examples of people using synthetics one day and then natural petroleum next day in their car crankcase engines, and how it turns into this thick, gooey molasses and their engines get killed. Okay, would not recommend mixing them if I can avoid it. Advantages of synthetics: great oxidization resistance, great reduced friction, a great velocity index, a viscosity index, so better low high temperature operating characteristics, generally a long life, 2-3 times what a regular petroleum oil would be. So if I've got a system that's getting a lot of hours, 8,000 hours a year or something like this, synthetic is absolutely worth it to reduce the amount of downtime I have to oil changes and things like that. Vegetable-based fluids, really popular. Superior biodegradability. Yeah, most vegetable oils biodegrade into something relatively safe, very safe to drink even. It says here soy, canola, and other vegetable-based oils have a high VI. You may think that we want to use peanut oil because peanut oil has the highest lower explosive limit of the vegetable oils, operates at higher temperature, but it's got a dreadful velocity index. So we tend not to use peanut oil. Hey, and you never know, maybe half the operators are allergic to peanuts and we'll get them sick. So in Canada, canola oil, rapeseed, we'll tend to use that to manufacture our hydraulic oil that is vegetable based. They do, wow, that's a really bad spelling mistake. Posses instead of possess, poor hydrolytic stability. i.e. the water beats up on it. And poor characteristics, low temperature, it tends to have a bad velocity index when the temperature gets really, really low. But for environmental considerations, we may want to use it. Example being the Olympics in Vancouver in 2014, the Green Games, huge amount of construction going on. So at Whistler, a lot of the equipment there would have vegetable oil for hydraulics in the excavators and things like that. If there was a leak, it was just a simple cleanup. Whereas if it was a hydraulic leak, yeah, everyone would be all over it. There'd be dozens and dozens of cubic yards of material that needs to be decontaminated, et cetera, et cetera. Vegetable oil, it's a leak, we'll clean up as much as we can and keep going. So the perceived damage was a lot less for that process. Now, notice the 200 gallons a day that your excavator was using in gasoline. They seem to think that having green oil was really, really important. As a chart you can go through here, just some characteristics with some of those properties, a little bit more detail on those. Hydraulic fluids, they leak, okay? 70 to 85% of hydraulic problems are associated with contamination or the improper choice and handling of hydraulic fluids. Okay, I'm not talking about hydraulic fluid problems. I'm talking about all hydraulic problems. Come back to the fluid. 70 to 85% of them come back to the fluid. Okay, poor design, poor choice, poor maintenance, especially that what I've seen in small to medium-sized companies in Alberta. Poor maintenance of the fluid. I've got to take care of that fluid. Okay, so proper maintenance, proper use of the hydraulic equipment is essential for long life and safe use of that system. Trained, informed operators and repair crews, as well as purchasing, design personnel is necessary for effective operation of hydraulic equipment. Don't let your purchasing agent push you around when it comes to buying the right hydraulic fluid. Any questions as I race through that to get time for this second slide deck, which I'm going to go through even faster. Chapter 6, okay, different chapter in the book, for contamination control. Let's have a look. So building on that last slide that I just had, a great deal is known about prevention and control of contaminants. It's estimated over 80% of hydraulic system failures are due to poor fluid condition. Actual failures, where things break, is because of poor fluid choice, poor fluid maintenance. A contaminant is anything in the fluid that shouldn't be there. It can be another hydraulic fluid. So when I add a little bit of ATF to my system just to top her up, I'm actually adding a contaminant. It really shouldn't be there. I should be probably using the right fluid, okay? So any contaminant will harm performance. Contaminants may be gas, they may be liquid solids. We want to take care of the fluid. A lot of investment should be made into taking care of the fluid in order to have long life of the equipment and safe operating conditions. So where does this contamination come from? It could be built in. When I make a system, there's a huge amount of contamination. I clean it, still some contamination. It could be ingressed. I could have brought it in there when I added the oil. Last week, we used those small hoses that we use to connect the load sense together. They're open at either end. There's a source of contamination. Okay, every time we put together a quick disconnect and take it apart, source of contamination. Okay, ingress contamination, or could be internally generated. As the fluid breaks down, as bits break off of our system, we could have contamination coming from those things. So new equipment has contamination. I've got a bag in the lab at the moment with 2 brand new hoses in for load sensing. If you look in the bag carefully, there's oil in there. The manufacturer makes the thing, they test the thing, they flush it with a cleaner, and then they flush it with hydraulic oil, and then bag it up with the hydraulic oil there. It acts as a preservative, acts to keep contaminants out. I feel a lot more comfortable buying a hose that has got oil all over it than a dry hose. I know one of them has a less chance of having contaminants in the system. So these new items, or any item that we manufacture, we create contaminants in our manufacturing process. Okay, I've got an example here halfway down. The assembly of 1 3/4 inch pipe fitting creates 60,000 particles over 5 microns. Okay, 60,000. That's not even the small ones that I really worry about in my high pressure system. 60,000 particles. This is stuff you can't see. You can't see something that small. Okay, we're going to get to that, but you can't see below 30 microns. There's no way you're going to see a hair that thin, or something like, well, if a hair could get that thin. These are small contaminants that will build up in our system and cause us problems. So a single part has got 60,000. So my whole hydraulic system, every component needs to be cleaned before I use it. It's going to be cleaned and flushed with hydraulic fluid in order to reduce the amount of contamination in my system. It can be brought in with the fluid. If I think of the fluid being made at a refinery, yeah, that's usually pretty good. We pipe off different hydraulic oils to storage, and then we blend them into another storage tank. Then we put them, say, into a truck. Well, who knows what that trunk last carried up. I bet they didn't clean it out. It probably had oil in it, but maybe not the hydraulic oil. It goes into a barrel. Who knows where that barrel came from. And then it goes into my reservoir. All places where we could pick up contamination and then transfer it into our system. So the new oil is usually pretty clean, but along the way it picks up a little bit of contamination. If it sits there and gets old, the additives break down. Now I've got another contamination. We've got to think about our life cycle of our oil and our process in order to make sure that it is suitable to go into stuff in the first place. Dirt, other particles often enter during servicing. So you guys are fairly full classes, so you don't see me service equipment very much. I have another class on Tuesday where I am often taking parts, valves and things like that, that have some sort of issue, to see if I can service them, fix them, or replace them. Every time I do that, I've got to be very careful not to allow fluid to get contaminated into the system. Got to reseal everything. I've got to tighten the valves back up properly. Cylinder rods, wipers, excuse me, they're not perfect. I'm going to get a little bit of contamination through those. That will build up over time. Internally generated contamination, there's a list here of types. Abrasion, that causes things grinding together. Erosion, much like a river eroding its banks. Fluid flowing through at high pressure, high velocity can cause erosion of metal parts or rubber hose parts. Adhesion, metal to metal, at a molecular level, things like to bond. Fatigue, just using it a lot. Okay. Cavitation, we talked about that one a lot as an enemy. Corrosion, we talked about that. And aeration, just getting gas in the fluid, not through cavitation, but through a bad seal, sucking it up into the system. So abrasion, 3 different types of abrasion. One is just something striking it. When you're chewing something, you chew down on a nut, it might damage a tooth, okay? Piece of abrasion. 2-body abrasion. That's for those of you who grind your teeth at night. You're just grinding away your teeth, wearing them out. 3-body abrasion, think of getting hit with that softball on the teeth, something else all in together, beating you up. These are different methods of abrasion and will cause damage in our system. They create more small parts in our system, more contamination to cause damage. Erosion, high velocity particles striking a surface, much like a river, except way higher pressure. Adhesion, metal to metal contacts. When we don't have enough lubricant, we get adhesion. There is galling and things like that that are going on, but I can get a piece of metal, the molecular bonds are orientated such that there's a slight positive and a slight negative between these two items, and I get an adhesion factor at a molecular level. Corrosion, we all know what corrosion is. Fatigue. Yeah, it's one thing being tired. It's another thing being tired when your muscles are damaged. Same things happen with metal. If I've got some damage, if I've got a little bit of damage, that's where damage is going to get serious. Repeated stressing of a system, and in a hydraulic system, repeated pressure application, repeated striking from small particles is going to cause more and more particles to break off and stressed. So we want to avoid fatigue. Cavitation, talked a lot about that in the last 10 weeks. As the bubble of air, well, in this case, vapor, implodes, it gets down onto a surface and then collapses. As it collapses, kind of digs in to the surface, causing a little bit of damage to the surface. Those points generally happen at very specific points within our pump, and it repeatedly happens in the same place time and time again. Ultimately, we're causing failure. How do we cause it? We can overrun the pump. That can cause cavitation because the fluid wasn't warm enough. A restricted line wasn't big enough to suck up the fluid. Restricted air breathers, if my breather on top of my reservoir gets clogged with dirt and bugs and whatever it is, it's going to not adjust the volume of air in that reservoir correctly, and that's going to cause cavitation. Plugged inlet strainers, the one at the bottom there, that's got to be changed every now and again, not as often as the other ones, but they don't have a check valve in them. So as that plug, they're trying to pull air through a smaller and smaller orifice, allowing for cavitation. And excessive viscosity of the oil can cause me problems. Now here's an example of cavitation due to a restriction. In the low pressure side, these bubbles aren't a big deal, they move through. This picture shows lots of cavitation occurring in this area in the pump. The reality is, where it says erosion and implosion, that's where 90% of the cavitation will occur. They occur at the transition from low pressure to high pressure. As I'm trying to create pump from the flow, I've got this negative pressure, depending on the resistance to flow in my system, a higher pressure downstream. But right at these points where that fluid changes to pressure state is where most of that cavitation is going to cause erosion, and then corrosion sets in. Aeration is just generally badly assembled parts. Okay, it allows the air to be entrailed or sucked into the system. Some of it collapses like cavitation, not all of it. So it's going to cause the same problem as cavitation for those that are collapsing. But as it passes through the system, air is compressible, hydraulic fluid, virtually incompressible. I'm going to get spongy operation, poor performance, slow performance of my system, and can cause a lot of noise. Okay, often we hear noise on our trainers of those bubbles moving through the system. There's a video here you can watch about aeration. Yeah, the bubbles moving down the system. Call it the silent thief. We have designed a system to operate at so many cycles an hour. We're getting less than that because of some air getting in the system. Therefore, I'm building less product. Looking at various contaminants, where do they come from? The top half are stuff that I will kind of accept as this is going to happen in a mechanical system. The bottom half, they're going to happen as the oil breaks down, and generally can be avoided by doing regular prescribed hydraulic fluid oil changes. Contamination control. If I control the contamination, I should be able to extend the life of it. Now, what does a lack of control mean? Okay, lack of control means the fluid is going to age quicker. The fluid is going to get used when it shouldn't get used. So it's going to be resulting in equipment being less useful, maybe damaging it such that it's obsolete long before the end of the project. MIT discovered that a lot of the time it causes accidents. Okay, 15% of the time I've got a contamination control issue, there are failures and accidents. Okay, our performance will drop off. I've got corrosion, mechanical wear, things like that. It amazes me that 1 in 6 of the issues was an accident. Sludge can form. Okay, sludge can build up within the system, especially if it's been idle for a long time. Sludge does build up in the reservoir. That's the only place I want to see it. Okay, because if it's there, it's not elsewhere in my system. So I'm just going to clean it out whenever I do an oil change. Bad lubrication. Bad lubrication means more heat, more wear and tear, things like that. Silting, really, really fine bits of contamination, micron, half a micron, things like that. Collect in certain places that we don't want them to collect, where the oil may not be flowing very fast, where it's acting as a seal. Okay, I've got a bit of oil acting as a seal, a high pressure system between two surfaces. The silting builds up there. Okay, what it will actually do is cause that seal to become too good. The oil doesn't flush through, and now I've got things starting to bind. I might have a varnish or something. I get sticky surfaces, poor performance all around. An idea of clearances on some of these items. Look here in the microns. Remember that part I said was 60,000 parts, contaminants from a 3/4 inch fitting? And that was 5 microns and above. Look how many of these things have clearances of less than 5 microns. Okay, all those other parts that we didn't even count are going to go straight through there. It's only a few of these things, like the piston pump and some servo valves, that I really have to worry about that 60,000. I've also got even these smaller parts that I need to worry about in my system. Big parts, hey, big parts generally don't fit through a tight space. That's good. However, big parts carry a bit of momentum when they hit a metal surface and start damaging it. Really, really small parts like silt pass through the system. They're still going to do some damage as they hit things. Particles of a particular size are going to do damage. This is why when we look at contamination, we're usually looking at particles of different sizes and rating how much contamination based on that, because my system can handle certain levels of accommodation of a contamination, but I should know what they are. Here's a picture showing a relative graphic there. There's the human hair there in orange. Okay, and then starting to talk about the size of things, a grain of salt being 100 microns, 74 microns for the human hair. Red blood cells, 8 microns. A red blood cell is a contaminant because it's too big in my system. Okay, loves to absorb oxygen as well. Don't bleed into your hydraulic fluid. So most of the stuff is too small for us to see. How do we see it? How do we capture it? We have to usually use specific equipment to do that, or just do regular oil changes. Failures can be catastrophic. Catastrophic implies, breakage, maybe someone getting hurt. Intermittents are a pain in the butt. Tracing down what is causing an intermittent failure. Spent way too much time doing that, or just overall degradation, just starts to run slower and slower, poor performance. Looking at a vane pump here. So I've got a vane pump here. Is it a pump or a motor? I've got fluid being pushed at high pressure, okay, to a low pressure application. So this must be a motor. And if I got a little bit of fluid up there right on the tip of that vane, it's fine. If I've got a little bit of contaminant, a bit of metal particle up there getting scraped, I'm doing a lot of damage. Just the same as if I had a small bit of silting or metal particle down here where the vane slides in the rotor, it might jam down. If it jams down, the high pressure fluid just sails on past the vane, doing no work for me. Okay. So there's lots of places throughout the system we can have problems. Gears have really, really tight tolerances, i.e. metal for metal surfaces. So I've got to be really careful I don't get contaminants in a gear motor. The most basic and simple one and most forgiving one are generally going to have bad efficiencies as they age because of the contamination control. Even in a piston pump, I might get contamination that it causes a problem, especially if it causes a jam in that piston moving in and out. Therefore, I get poor performance. Right in the valve, I've got here a detail showing some silt. Most of the silt will pass through. But if this valve is sapped, say we've gone and done a summer break or something like that, and it's sat for 2 or 3 months, that silt is going to build up and become incredibly sticky like gum or varnish, and I may not be able to transition the valve from state to state correctly, or it may just get slow. A big particle that's just small enough to fit in there, that's going to grind away at these surfaces, okay, until it's ground them away enough that it gets blown through and off the tank and off to the filter. Generally eat away at that point where the orifice would close, okay, right at those 2 points there, or same on the other side, is where I'm going to get my erosion, my corrosion, and poor performance, because it's going to leak more fluid all the time. How do we sample it? Generally, I'm going to sample this and send it away if I'm running a sampling operation. I want to sample the fluid in use. Generally, I have a specific port or something where I can draw a sample of the fluid while it's in use. Say an air bleed valve on a big cylinder is a good place to do that. I put a different type of seal on that so I can draw out working fluid and send that away for a sample. No good sampling it unless I know how clean it should be. I need a contamination control program. Now, I send it away and I can get it a report back, usually within a few days here in Calgary, on how dirty my fluid is, what the contaminants are even. Generally, I'm mostly interested in the size of the contaminants, and that can be done different ways. There's a flow decay screen. What is the pressure drop as the fluid go across that? We can use white light. We can look at the fluid with a white light and an analyzer. We can use a laser down to 2 microns, see really, really small stuff, see how much contaminant is in there. But below that, I don't really have a good way of measuring that. Okay, and this equipment is expensive, so it's not usually in-house. We'll send out for a sample. Now, this you will need for your next quiz and the final exam. ISO contaminant code. Now, the standard for this changed, well, maybe about 15 years ago. I doubt you're going to see the old one anymore. What we look at is the number of contaminants at 3 particular sizes. Okay, well, range, it's a range, okay? The number of contaminants at 4 microns, 6 microns, and 14 microns is the standard that we use nowadays, okay? So what we do is we measure the number of particles per milliliter of fluid. Okay, so if I've got anywhere from 13 to 2,500 particles that size, this is in range number 18. Okay, if I've got that many particles in the 4 micron size range, gives me a number 18 number here. My cleanliness node is 3 numbers from the smaller particle to the larger, 4, 6, 14 microns. A manufacturer will tell me this is the appropriate cleanliness code for my fluid, or better, that I need to use for my piece of equipment. So I need to design and maintain my fluid to a particular cleanliness in order for it to perform as per my manufacturer's recommendations. This is something you're going to have to come back and have a look at closely and look on the text closely. Don't get confused in the text. I believe the text still uses both the new and the old standards, or at least revision 5 of the text does. Here's an example of recommended cleanliness, generally, depending on how much pressure you have in the system. Okay, so a cleanliness code, okay, a range of 20 for 4 microns for a fixed gear pump, 18 for 6 microns, and 15 for 14 microns, or better. If I go back to that chart, what was that? 20, 18, 15, 20. I can have between 5 and 10,000 4 micron parts per milliliter. I can have a lot. of contaminants. Okay, 2018 and 18, so between 1300 and 2500 with the 6 micron, 15 between 160 and 320 fairly big parts of 14 microns. So these numbers here on the range number indicate the cleanliness of my fluid and the designed cleanliness. Okay, so a lot of operations, important operations, will have fluid sent out and analyzed on a fairly regular basis. I can take this while the machine's even running, no downtime required, to see if I should be changing my fluid or not. The way most of us do it here in Calgary, we just do regular scheduled oil changes. We tend to waste a little bit of money on fluid because we're changing it more often than we need to, but it's cheaper and easier than otherwise. Now, that being said, my cleanliness code is in ideal operating conditions. If I frequently start below -18, hey, welcome to Calgary in winter. Intermittent operated with temperatures over 160 F or 70 degrees Celsius, maybe not so much. High vibration levels, so high system shock operations. Yeah, welcome to mobile equipment. If I have any two of these present, I need to improve the cleanliness code requirement by 1 for each of those ranges. I need to run cleaner fluid, okay, in my system. I make the assumption is that my fluid is going to be dirtier. Well, it's not dirtier, it's just I'm operating in a more harsh environment than we would really like to. Therefore, I need to run cleaner fluid. Our contamination control, well, what can we do? We can filter it offline. Okay, we can flush the system, we can put new oil in. One way of helping produce contamination control, we put a filter on our air reservoir. Okay, that cap at the top has a filter that we need to keep clean. Okay, now it says here a 3 micron filter is used nowadays to keep it clean. Okay, that's a filter that's going to need changing and cleaning fairly often in order for it to perform correctly and let all the air through. The one in the reservoir, it's fairly a big thing. We don't want to have a lot of cavitation, so we're only picking up the big parts here. Really, most of the small parts should have been picked up by the earlier filters in the process. Earlier filters, now we only have those 2 filters in our process. We have our filter on the inlet, the mesh filter, and we have a filter at the return to the tank. In a high pressure application, I usually have another filter right after the pump, right before the pressure relief valve. I filter fluid here when it's kind of warm, it's under pressure, and it's about to go into my system, go into those tight clearance operation valves. So generally I have actually 3 points in my system that I filter within a closed loop system, not the 2 that we have in our lab. Hard thing is it's got to operate at high pressures and it's got to operate at high volume for the whole system, and a bit of temperature sometimes. The return line filter we have in our lab, we've talked about those, how do filters work. The return line one will have a bypass in so that if the pressure builds up in the system, it's not thieving pressure away from my working elements, but still as much oil as I can is getting cleaned. With that high pressure line, no, we don't bypass any of it. It's all going in and out, get it clean as possible. It's going to be more heavily monitored. In our lab, we have a little indicator on our filter. So the symbol, we have not been using the actual correct symbol in our labs. We've been avoiding the little indicator symbol there, the round with an X in it, an indicator of some sort to say that the filter needs changing or not. It might be a pressure gauge, okay, or it might be just a color system that we have. Who knows what it has? It has some sort of mechanism to say, oh, filter needs changing. So that's actually very common, especially with that high pressure application. Contamination control can be done remotely, externally. Okay, I might have a secondary system that sucks oil out of the reservoir, cleans it and dumps it back into the reservoir. Okay, that is an option for a system that has maybe lots of pumps. Some of our systems, we might have 4 or 5 different pumps delivering oil to different parts of our system. We will often have an auxiliary cleaning system, contamination control system, that is going to clean all the oil instead of relying on 5 little independent ones and maybe one of them working too hard, etc., etc. So it's quite common to have a separate filtration system in a large hydraulic system. Filters, okay, they have a beta ratio, B. There's a list here of what that means. Basically, how many parts per 100 does it filter out at that size? So it has a size, i.e., I'm going to filter out 5 micron parts or 20 micron parts, and then how good is the filter at effectively getting rid of those parts? Okay, so the efficiency ratio of that. So, a beta ratio of 100, okay, gets 99% of the stuff out, but that's meaningless without knowing how many microns that filter is designed for. Okay, often in systems we'll have multiple sets of filters. It's very common to have 2 or 3 filters. The first filter being catching larger parts, and the second smaller parts, and the third really fine parts, to not have a filter clogged very easily of really, really fine silt. So we might have multiple filters in an operation to take the parts out to extend the life of the filters and the system and change the time between filter changes. We can have absorbent materials. Okay, we trap particles by mechanical means. We typically do not use a chemical system in order to trap things. For instance, bentonite slurry is a common filter mechanism in a lot of drilling applications here in Alberta, but that is not suitable for a system like hydraulics. Typically, we're going to use some typical filter medium, much like you might find, say, on a home swimming pool, or a paper filter that you might have. Think of what's on your coffee filter, except pretty sophisticated compared to that. It's going to be pleated, it's going to have multiple layers, it's going to have some sort of mesh to support it in order to catch the particles out of the hydraulic fluid so they don't get cycled through your hydraulic system time and time again. Questions. What's the objective of a hydraulic fluid contamination control program? What is a hydraulic fluid contamination control program? And it is amazing how many businesses in Alberta don't know what that is. I need to know what is acceptable for my cleanliness of my fluid. What am I doing to ensure that that fluid is clean enough? Remember, 85–70% of my failures are due to not having good fluid. So I should have a control program for that fluid. Okay, so even large multinationals often don't have this everywhere. Aerospace of Honeywell, yeah, they had a great program, which I could borrow and then implement in Honeywell Life Safety. Didn't have a contamination control program. Okay, so most places you guys are going to go and work at here in Alberta don't have one. Even if the control program is saying we're going to have to change the oil every 6 months, at least that's a start, something. Okay, so what we want to do to achieve and maintain a cleanliness code level of purity in hydraulic systems, okay, we want to be able to do that. That's the objective. How clean does it need to be? How do we keep it that clean? Okay, describe hydraulic fluid contamination. Pretty much anything that shouldn't be there. The presence of foreign matter within the fluid, gas, liquid, solids, which may or not be visible, even other hydraulic fluids, the wrong high fluid. What does the symbol represent? It's the filter. It's got the bypass check valve, and it has an indicator. Any questions? Now, this question, we've seen it all before a couple of times. I'm going to go through it again, maybe solve it a little differently than maybe the text would have it. I've got 2 cylinders interconnected. Okay, and I needed that pressure over by the shutoff over on the left there. Now, what I do when I set this up is I think, okay, I've got a force at one end, and it's going to cause a force on the second or the first cylinder. I've got a pressure at the end I need to calculate, and I've got an intermediate pressure that I could calculate and measure between the two. So I set this up knowing that this is the environment and this is the measurements that I need in my system. What happened here? Excuse me while I argue with my pen. Where are my pen controls? I'm going to reduce that and the Microsoft solution of opening it again. Where did my pen controls go? I don't know. I'm going to move on without it then, because I don't have a lot of time. Okay, so I said we're looking for this P at P1. I just called it P1, pressure gauge reading. The force, and that's wrong, that's force at 1. Force at 1 was 26,500 pounds. Diameter of cylinder 1 at the cap end was 10 inches, etc., etc. So I extracted this information, and my equation that I'm really going to be interested in using is F equals PA, but which pressures, etc. If I rearrange that, P1, let me have a look at there. P1 is equal to F1 over the area of cylinder 1's cap end. Okay, I can calculate that. F1. No, that should be F2. Yeah, F2. Confused between 1 and 2. F2. So F2 we don't know. F2 could be calculated as P over A, the PA. So that would be the pressure at 2. Area 1 annulus. P1, P2, P1, P1. Okay. Now P1 can be calculated as that force at 1 divided by the area of cylinder 2's cap. Okay. So if I put all those together, I get that pressure at 2 equals force at 1 over area 2 cap times area 1 cap multiplied by area of 1 annulus. Okay. Yep, okay. So what does it equal? 26,500 pound pi over 4 of 10 inches squared minus 5.5 inches squared. And I've got those bottom two. 4 of 6 squared times pi over 4 times 10 squared which equals 654 psi. Okay. So I tend to formulate a formula instead of solving it individually along the way, and then pump all the numbers in to get a final answer that should be less error prone of 464 psi. 2. What is the cylinder? What is the GPM required to cycle a 5-inch cap, 2.5-inch rod, 30-inch stroke, double acting cylinder in 30 seconds? Cycle means extend and retract, all within 30 seconds. So we're looking for a flow rate. We've been given diameter of the cylinder and the rod, a length and a time. So my net equation, I'm going to have, I called it just Q into the cylinder in total, is going to be the Q of the extension added to the Q of retraction divided by time. So what I've put down is a calculation. What's that actually going to equal? Q of extension. So I need an area. Area times, okay, so 5 over 4 times 5 inches squared. The length is the same both directions, so let's just add those two together now for the extension and retraction. Cap end minus the rod end times the length. What's that, 30 inches? Over 30 seconds, which is the time. I need to convert this seconds to minutes. 60 seconds per 1 minute. The seconds will cancel out. I got square inches cubed on the top, so 231 inches cubed on the bottom per 1 gallon. To get an answer of 8.92 gallons per minute. 3.
We wouldn't do 60 inches in this case. We just still consider the 30.
Yes, I've gone 30 out and 30 back again. I could have done this pi over 4 times 5 inches times 30 to give me the volume on extension. And then I could have gone on the pi over 4 times 5 inches squared minus 2.5 inches squared times 30 to give the volume on retraction.
Gotcha. You just took it out.
Yeah, I just pulled the 30 out just to try and eliminate the math a little bit. I could have pulled out the pi over 4 as well. Okay, I would have saved me a few keystrokes. Okay, what head pressure is developed? We've done this one before at sea level. If an overhead stacked reservoir is 3.2 feet above the intake of the pump, the specific gravity of the hydraulic fluid is 0.93. Okay, so how much head pressure do I have on a wet pump? Head is what we're looking for. We know it's 3.2 feet up above that. I'll keep some people happy. Specific gravity was 0.93 in water. Density is 62.4 pounds per cubic feet. So head equals height, 3.2 feet. Times the specific gravity, times density, 62.4 pound per foot cubed, times the specific gravity, which is unitless. Head is in PSI. I have a pound, but I do not have square inches. 1 foot cancels out with there to convert foot squared. I need to have 12 for 12, 144 inches squared, and that will give me pounds per square inch. Excellent. All that equals 1.29 PSI. Okay, yep, that should be good. Any questions? Question 4, this is the one that people may have a problem with. What is the force on extension of the clamp cylinder? The important part to note here is this pressure reducing cylinder. The maximum pressure in the circuit is in the clamp is going to be defined by that 900 psi. The maximum pressure in the punch circuit is going to be defined by the 2000 psi. Okay, so this is a common mistake when people see this question, is choosing the wrong pressure. So our pressure is going to be 900 psi. Diameter of that cylinder was given as 12 inches. So this is a fairly simple force equals pressure times area equation. Now that we know we've got the right pressure. So what have we got there? 900 times pi over 4. Oh, I'm rushing. So 12 equals 102,000 psi. 102,000 psi. Okay. Describe the DCV. I always start with the center. Well, no, I don't. I start with the 3 positions. Okay. Really, I tend to forget that sometimes, so I should start with 3 position, 4 port, closed center. It's solenoid actuated. And it's spring centered. Yep, that's all I can say about that valve. Okay. A 6 gallon per minute pump supplies a double acting hydraulic cylinder with a load of 27,500 pounds on extension, 18,500 pounds on retraction, 5-inch diameter cylinder with a 2-inch rod and a 40-inch stroke. What is the GPM? So Q extension is what we're asking for to extend in 40 seconds. So I've been given the diameter. That force is, those are just red herrings. I don't need anything to do with force here to calculate GPM, because I want to calculate my flow rate, which is the volume of fluid I need to pump over the time of that. So what's it going to be? A volume is going to be an area, and it's on just extension. By the length, which was 40. With my time for extension was 40 seconds. Gallons per minute, inches squared plus another one's inches cubed, so 231. I don't even remember usually half the time what these equations are. It's just I look at the units and then I know it should be a gallon over inches cubed. 60 seconds per 1 minute. Since I've got the units cancel each other out, seconds cancel each other out, all the 40s cancel each other out. That gives me a short equation, 5.1. Go back and check. Wasn't a trick question. It's less than 6, therefore 5.1 gallons per minute. That is it. Any questions? Nope. Okay, thank you very much. I will see you in lab next week. Remember, you be prepared to do either lab 11 or lab 12 next week, and then vice versa the following week. Okay, thank you very much.